Hi, this is Claudio from Explicit FEA again. Back today with a tutorial, a free, relaxed live session regarding how to simulate bearings in ANSYS workbench. Let me firstly share my screen. I apologize since the very beginning if I am a little late because I am in the beginning of this streaming job. And yes, let's go towards bearings. Meanwhile, I'll open ANSYS workbench. A quick reminder about my website: simulations, books, tutorials, whatever you want, whatever you need, you can find in there. Also, we have a contact page. You can email us, and we will help you as quickest as we can. All right, so a few words regarding bearings. We all know what they are, of course. In principle, they answer the need of attaching to cylindrical faces. And in touching these cylindrical faces, we need a gap, we need surfaces that will not corrode, erode, will not wear, will not overlap, interfere, collide. So we opened the ANSYS workbench. Let's do this in a very simplistic way at the beginning. As I told in my first stream, I'm interested in keeping things very clean, clear, and easy for beginners in FEA and ANSYS. Afterwards, each to his or her own desire, they can complicate, make the things more complex as they wish, or according to the design that they receive and they want to simulate. Let's go to space claim and kind of design bearing, okay? Do we have a cross section? Let's see. So this is what we will do in principle. We have an outer race or an outer cylinder, an inner race, inner cylinder, the ball or the roller, the element that rotates. Then there is a cage which holds all these balls together and at a certain distance, let's say. This is what we will do in principle. Here is the cage that holds the balls together. You can notice that they are, let's say, above the center of the ball. Okay. So in principle, this is what I will do. Let's do it. We have a plan view. What would we start with? Should we start with the ball? Should we start with the ball? Why not? Let's see if I can make an axis just for fun. Can I make an axis? Yes. So we have an axis, okay, here. Because I would like to make a rotational, a circular pattern of balls around this axis that I just created, okay? Escape, exit the command. Now let's go to sketch and access the plane view. I will move this towards my image. All right, so all fine and dandy. let's click if we have here a sphere. I have no idea about the dimensions right now, but we will see them. 7 millimeters. Yes. It's cut because we have like a section view here. Escape, return to 3D, and we have our first ball, okay? So in order to keep things kind of realistic, let's move a little. And if possible, let's pattern this ball, okay? So we have a circular pattern. Select objects to create the circular pattern. This is what I will need. Select linear axis and so on. We select this axis. And look, we have here 8 balls. I'm a little counting and meditating if we need so many balls, because we will have to create the contacts manually. Yeah, let's do it. So we have the balls. Okay, so let's create now those races, okay, those small cylinders. I would click this axis and let's create a plane. Right, so the plane goes like this. We can create the cylinders like a rotational sketch, but we will do the easiest way. We will rotate, okay? So let's make it planar, let's say. Let's make the plane planar. All right, you understand. Double click. Undo. What happens here? All right, this is what I wanted to do. Why? Because I will come from above, go to sketch mode, and here I will do those, I will make those races, all right? So this will be the inner race. Let's make it 24. And there will be like a groove for this race. Let's make it how much? 28. This will be the inner race. I'm wondering if I need to make both races in the same sketch. Yeah, why not? Let's do it. I am the partisan of not complicating things. So 37 here, and the last one we don't really care too much. 41.5. Yes. Return to 3D mode. And here you will understand what we do, yes? We click no merge. We select both faces or surfaces, and we will extrude them, yes? Let's make a guesstimation, something, undo. We use this option, pull both sides, yes? Yes, something like this would look nice. Let's make it 8. All right, so we have the races. In principle, they should not be merged. Yes. What will happen now is, let's make also the very simple cage. Again, on the same plane. Sketch, and you know what? Let's make it a little thinner. Let's see together. So we're selecting these bodies with Control pressed. Make them transparent in order to easily understand what happens. I would like for the groove or interference to be, let's say, thinner. This means I will push this to be 13.5. All right. Enter, and this one, you'll understand why, because I need to give more space to the upcoming cage. There will be a cage and it needs to have space between these two races. All right, let's make the grooves in order to easier understand what happens. I will click the axis, escape, I will click the axis, then go to design sketch mode. Yes, so in principle, what I can do, the easiest way is to project. I can project this circle. Yeah, let's do it. And I will rotate, cut. I will rotate, cut both these races. You will see in a few seconds. Return to 3D mode. Now I have this surface. Look, this one, and I will rotate, cut it about this axis. Yes. So let's at this moment, let's kind of hide the balls. Yes, and let's make that rotation, that cut. Because we will need to have a gap, an allowance between the groove and the ball, we'll need to increase a little the diameter of this disc. Yes, just a little. Okay. How much? 0.1 or 0.05. Let's see with 0.05. So let me make the revolve cut, and we can easily see what's happening. Select an axis to rotate about. This is the axis. Select the faces, this one, and I will say cut. And yes, let's go to the end. Yes. Let's, we have the cut, right click, show all bodies. And now we can easily go, and see those, the allowance, the gap that I left between the ball and the groove. Let's rotate the plane, this plane, move, and rotate it like this, because I would like to see this, the section view. Because it is already selected, we go for section mode, and here, look here. This is the gap that I told you about, yes? Yes, a thing that I would like to do at this moment is to round this edge, these edges, the 4 edges of the grooves. There are multiple methods. One of them is this one. Let's click pull here, and we will select, no merge again, we will select this point with control pressed, we will select this point with control pressed, we will select this point, we will again this point, and let's drag a little. 0.35 looks very nice. You can see now the filets or the rounds. Okay. The same thing happens also here because it's we have 360 degrees. We kind of have the basis of a bearing, of a roller bearing. Let's create those the cage. So I assume we're in section view, but we're not. Let's click sketch mode. Yes. So do we care about reliability? And all right, what we learned from this from these drawings, we learned that the cage should be bigger or overlap the center of the roller. All right, you can see that the cage is above the center of the roller or the ball above. This is what we need to take into account when doing this this cage. Let's project a little this edge and also this edge, and let's come with this, and as I said, above, yes, beyond the center. So I will not make a symmetry around this point, the sphere center, but I will go above. Now let's trim what we don't need. We don't need this portion. I don't know. Why does it delete everything? Ah, yes, no, incorrect command. This is the trim command, trim. We will zoom out a little. Remember, control middle mouse. We will zoom out. Control middle mouse, shift middle mouse. These are the moving commands. Let's go to 3D mode. We have in principle this rectangle, which is the basis for the cage. Let's do again. Let's perform the revolve cut. Revolve, select an axis. This is the axis. And cut. And let's make it until the end. Of course, I forgot to hide the balls. Click the pattern to hide it. And now let's make this. Yeah, it's a very rough cage. I will admit it. Right click, show all, and we have the balls. All right. What we can do now? Let's cut out, yeah, the balls from the cage. Something like this. Yeah, there is a small reminder in my head to save what I'm doing. We'll call it stream 2. January 2nd, bearings. All right. Should I check the stream or not? Does it? Yes, as supposed. Where were we? Here. Let's make. We have the command, the combine command, which is responsible with the Boolean operations. Click a target object. I need the cage to be cut with the balls. If I click one ball, because they are in a pattern, all of them will be selected. Okay, let's click one. And now the cut is complete, okay? Click regions to remove. You understand that there are now like small disks pertaining to the cage. So we need to kind of remove those small disks. Either we exit the command and do it manually and slower, but if we hover, we can see like a pinkish region. Believe me, this is exactly what we need. This disk, we need it to be removed. Let's do it. Click here, and also here, you see it inside. Also here. Also here. 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 If you did not understand, just exit the command and delete these portions from the cage. These leftovers, delete them manually. Okay, if you didn't understand what I did, what I performed here. Escape. Now let's check if we have everything in order in principle. We select the plane, section mode. Look here. So it's more than nice. I like it very much. What I would like though, remember about gaps, about allowance. So we need to have gaps also here in the cage for the balls to move freely in the cage, okay? Let's find a method for these cutouts. Let me show you the cutout. We need to make these cutouts larger. All right. So the easiest way, in order not to think too much, is to click each of these cutouts with Control pressed. This is the easiest way. And instead of 3.5, let's make them 3.55, the radius. Yes. And if we look in section mode, look how they appear. Right click, show all in order to have. You see, these are the allowance or the gaps. Now, according to my taste, they are the allowance or the gaps is too big. What we do now, in order not to change all the cutouts on all the grooves and etc., let's change the diameter of the sphere. Maybe 3.55, and hopefully it will change in the entire pattern. Undo, Control Z. Let's go here with no merge, 3.52. 3.52. 3.535. Yes. No, I like it very much. Sincerely, again, I also would like for these two edges, yes, to be rounded. These edges for each cutout pertaining to each ball. How do we do it? Let's hide other objects. Click on the cage, hide others, and maybe click here. Go to selection, and we have edge chains with same length on whatever. Yes, they are selected. We can just drag a little to have a radius. Yeah, 0.2. It's more than enough at this moment. Let's do the same here. Select one edge. We go to selection, edge chains with same length on whatever. We see they are highlighted with orange. I don't want to drag. I will just type 0.2. So right click, show all, again, section view. Look here, they are very nicely round. Also here, I believe very much in this model, in this, I would not say design, but model, and I know what is inside it. Pay very much attention on the things that you get from GrabCAD or other websites, because they usually have collisions, they have lots of interference, and they do not obey the laws of common sense and of engineering practice. Not saying that my model is 100% professional, but it serves the purpose of today's lesson. So, do I need to do something more at this moment? Let's not complicate things. Let's stay with what we have. All right, save again. And yes, let's not elongate it too much. And double-click model. Let's perform this simulation. All right. We'll do it in static structure because it's easiest and quickest, in my opinion. In static structure, you need to remember that time has no physical meaning. The so-called time steps are like milestones to apply the boundary conditions, let's say. So the loading of a 3D model takes some time because I closed the space screen. Remember, for a zoom extent, a quick zoom extents, click F7. This is our bearing. Very nice ball bearing. Geometry, material, structure, steel, we don't care at this moment. F2, rename ball. This will be, I like to call it inner. This will be outer. This will be the cage. Everything made of steel, we don't interfere there. Contacts. Let's see what ANSYS gave by default. Right-click on contacts, rename based on definition. And we have the contacts between the ball and between each ball and each race and cage. All right. So what we need to do now, of course, opposite to what exists now on YouTube, 90% of the videos, 90%, there are a few videos with bearing simulations, they forget to change the type of contact from bonded to frictionless or frictional, and they try and rotate the bearing with bonded contacts, which is laughable and sad at the same time. I will not comment too much. Also, they're doing this because having nonlinear contacts, frictionless or frictional, is very hard to master and to make the FEA converge. There is some philosophy. The easiest way, and where we will not care too much, is to have the contacts with the cage, to have them frictionless. We will get this out of the way. All right, we don't really care too much about those contacts. Where we will care is what will happen, what will occur between the grooves, the race grooves and the balls. So this being said, I would like to group all these contacts in a separate folder because we'll change their properties often, I think. So group balls and races. All right. It will be easiest to select them. So with Shift and Control pressed, we have all these contacts. Let's go and. There is some discussion to be made here. In reality, for example, this image, okay? Can I open only this image? Let's see. Yes, only this image. In reality, the purpose of the cage and of the lubrication and of the bearing is to reduce the friction. Normally, we will need to use either a frictionless contact between ball and everything or a very small friction coefficient. In reality, the ball will not rotate every time. The ball will not be, let's say, meshed or, how do you say, it will not be moved or rotated due to the race's movement in reality, because the purpose of the bearing is to have as much as a frictionless contact as possible. But because we will only rotate a few degrees, 90 degrees, maybe 180 degrees, we will need to impose a higher frictional coefficient than in reality, because we don't have lubricant here, and we don't have reality, and we cannot, and we will not perform hundreds of rotations of the entire bearing in order to see some rotation of one ball or of certain balls. So what I'm trying to say is that we will need to impose some friction in order to see rotation of the balls during such a small rotation that we will do. Because in reality, let's see how the bearings rotates. Let's see if we find what we need, all right? I don't know. So the races rotate, but the balls are not mandatory. They are not necessarily supposed to rotate. The balls are like a small support. They sustain the gap between the races, let's say. Yes? I hope you understand what I'm saying. I'm preparing the excuse for using frictional contacts. And because we cannot afford to have such too big frictional values, let's try and at this moment run with maybe 0.05 friction coefficients. between each ball and the contact pairs between the ball and the outer race, the ball and the inner race. Let's do it like this and see if the balls rotate. Will not change at this moment anything in the default settings. Right click, generate mesh. Yeah, so the mesh is pretty coarse. I will come back to this drawing. So we'll need a friction here. In order to impose a rotation, we'll have like a sticking state of the contact. In order to impose, to force the ball to rotate, also we'll need friction here. All right. In reality, there will be lubricant, there will be less friction, because the purpose of the bearing is not to rotate the balls. Yes, we'll need to have as much as friction as contact if possible in reality. But for the purpose of the simulation, we'll need some friction in order to make it move from this portion and also this portion. At this moment, we will use the same friction coefficient, but maybe it will be better if we use a higher friction coefficient on one side. We will see. We will see. Firstly, what I like is to have kind of the same meshing method. So I would like to change the races to be also tetrahedrons. Yes, because they are hexahedrons and everything is tetrahedron. Let's change these two regarding the method to tetrahedrons. Okay. We will generate mesh again. It will be very coarse. And in order to avoid problems, what we will do? Let's get a feeling about the sizing. The sizing is around, so the sphere diameter, if I remember, is around 7 millimeter. Let's make a meshing, an element size around maybe 1.5, maybe 1.5 for what? For default, for everything. Or maybe 2. Generate mesh. So it's not enough. Maybe I was inspired with 1.5. Generate mesh. I will look a little on the stream to see if there are questions. I don't see questions. Maybe they're not. So we are gradually getting there. 1.2. Yes, can we go to 1? Yes, let's go with 1 and forget anything else. You'll maybe ask, hey, Claude, why do you make them so coarse and about Hertzian contact? And at this moment, we only need to have very fast, quick iterations. This means we need to have a coarse mesh. After we have obtained a very nicely moving and rotating bearing, then you can choose to refine the mesh and make it more decent looking. But at this moment, let's make quick iterations, and we'll be satisfied if everything rotates according to what we need. All right, let's make this once. Only the balls I would like to refine their mesh a little with Control pressed, sizing, and maybe 0.8. It's not such a big difference. You know what? Let's also change the cursor. Right click to face, Control F, because I would like to refine only the grooves. The groove mesh density, all right? So here, let's make it 0.555, and also for the body, 0.555, all right? Right-click, generate mesh. It's a guesstimation, it's from an airplane view, but you see that it begins to look very professional. Right-click, rename based on definition, right-click, rename based on definition. They don't tell us too much, 0.6 maybe, and again 0.6. All right, at this moment I'm just being picky. Statistics, 175, oh my God. Oh my God, 175. I would like to fit. I would have wanted to have it below 100, but yeah, we will see. Let's see how much time it will take. All right, let's save. And regarding the rotation and the movement, what do we rotate? Bearings normally they are encased in something. Bearing housing or something, yeah? Yeah, so they are encased. So normally here, if we have a shaft, the shaft rotates, yeah, the inner cylinder, and the outer cylinder, the outer race is kept fixed by this small housing. So let's rotate the inner shaft. How do we do this? There are multiple ways. The one that I like very much is this one. Let's go for body ground and select a revolute joint. I will click this face, scope, apply. The rotational axis is Z. We'll have rotation, RZ, rotation about the Z axis. You'll see in a few seconds the corresponding circular arrow. All right, we can also at this moment do something like this. Click this face, body ground, and fixed to keep it fixed. All right. And regarding this cage, we can either select body ground planar joint, or we can input a frictionless support. Let's make a planar joint. So I will select these two faces and click here. It will be a planar joint. This means we will have translation on the X and Y plane. We'll have translation X, translation Y, and possible rotation about the Z-axis, which is what we really want. So these are the general directions of movements. They are not, let's say, loads. They are individualizations of the movements. Let's say they're not 100% boundary conditions. We don't have prescribed loads at this moment. All right. Here, each joint cuts and removes some of the degrees of freedom. Let's now go for the loads, and you will see in a few seconds what I'm talking about. Joint load. The only load that appears at this moment in this simple tutorial is this rotation. Yeah. Why does it want to put it here instead of here? We don't care too much. Yes, it's just a detail. But we know it rotates about this z-axis. Okay. Type, we will apply a rotation, which will be an angle. It does not make sense to say velocity or acceleration because these take place in time, and in a static structure simulation, time does not make sense. Magnitude, tabular. All right, so according to my experience, let's make maybe 4 steps. We will gradually increase and apply the rotation, gradually. Mandatory large deflection on, because we have a mechanism here. Solver type, direct. Let's apply the values. In order for you to see the tabular data, let's check a little the positioning of the on the stream. All right, I will just drag this here and make it how much? We'll be greedy in the beginning and say, you know what, make it 25 and 100 in the end. Yes, 25 degrees step. This is the only load, believe it or not. Yes, because we fixed. Now we rotate and we let the cage will be, let's say, meshed or pushed by the balls. We don't apply rotation, we don't apply anything. This is a very decent way of explaining and simulating bearings. We don't apply a rotation on the cage, we don't apply rotation here, we don't force anything. Because we rotate this, due to friction, we'll mesh with the balls will rotate and push the cage, and the balls will also push and rotate the outer braces. All these because we only impose this rotation and we let the friction do the job, okay? This is very decent and, let's say, conformal and kind of realistic scenario. Results, deformation, these are for the live results during the solving. Right click, switch to automatic mode. Solution, deformation total, strain, stress, and also very nice and important to see the contact tool. This will be very nice. Friction next stress, pressure, sliding distance. Why not? Let's put so many things. Penetration and gap. All right, solve again, and yeah, let's give it to play. Give it to solve. We, at this moment, we leave everything program controlled. This means we let ANSYS do its best to perform this simulation. For the number of cores, according to your physical cores, yes, solve. Let's see if it works. We're looking here for solver output, if it works. Yes, it started. We'll then change to forced convergence. And yes, let's wait to see how it behaves. All right. Again, let's look on bearings. There are lots of there is a lot of knowledge and courses and lectures and yeah, I didn't invent a ball bearing or something like this. We teach them. We learn them in the faculty or high school, trade school, whatever. So this is not a bearing PhD dissertation right now online, This is not the bearing mastership, mastercraft simulation and something else. Is just a tutorial for beginners, something very quick, very fast, very easily explained, and hopefully very clear to understand for anyone. Okay, so if we are here until it will converge, yes, this is a sign that the default time step is too big. Okay, so we'll need to have some patience. Until then, let's look at what our colleagues have done regarding bearings. This should be very interesting. So we have this user with multiple scenarios. Let's look at the contact region. Look here. He changes from bonded to no separation. Wrong. Completely wrong. No separation is almost bonded. It's bonded with some movement. So exactly in the first second, if you have no separation, why do you insert level or joint? Pressure 10 bar. Pressure on what? All right. Let's see. Joint. He creates a fixed. Oh my God, he fixes the races. Both races. Ah, no. He fixes one relative to each other. In order to move in tandem? Oh my God. I predict that there will not be a good result. But he has the speed, a very good speed. Sizing and control, the speed is very nice. He has a displacement? What? A displacement on the inner race? Displacement for what? 0, and he restricts the inner race from moving in the x and z directions. Oh my God, oh my God. A pressure, why do you need the pressure? An outer pressure. And he has here something very cute, displacement free to rotate. What? This is the displacement that he applied, but I would say that it makes no sense. Let's see the results. Who am I to contradict? Hex dominant method. This is very, very nice, very cute. Not tetrahedrons as I usually use. So we have results. Let's see the animations. Yes, as I was expecting, nothing moves. This defeats the purpose of a bearing. Nothing moves. You can argue, you know, Claudio, he fixed and he put the pressure and he wants to see the pressure in the ball bearings and the entire assembly without any rotation. You can say this, you can find excuses, but No, not according to me. All right, let's see this colleague. He did something, yes, he solved it until the end, but let's see what he is doing now. Meanwhile, while checking here, yeah, it does not look good. So let's stop, because I don't want to wait so much, and I don't want to keep you waiting. Nevertheless, this is a live presentation. Feel free to pause, skip, jump where you see the results. Nobody forces you to watch the entire thing. And I would like now to impose some time steps. Let's see. I like the time very much. Carry over time step 1. Initial time step. Let's make it here 0.1, 0.01, and 0.1. Remember, seconds are not, let's say, true in static, okay? Because time has no sense. But they are just divisions of the entire simulation, of the entire solving, okay? So save again and solve. Will it solve? Let's see. I think it solves. Solver output, yes, we have the live log, distributed domain decomposer. First convergence. Okay, I am confident it will work. So this colleague of ours, he has parts, contacts. He's selecting all the contacts, and please change from bonded to something, please. To not separate. Come on, why? Why are you doing this? Why? Ah, this is a copy. This is a copy. What? A copy of the other movie? Let's see. He makes a revolute joint on. He's applying a revolute joint. Oh my God, he likes to select. Oh, why do you select so much? Why? He applies a revolute joint here. Yes. And another revolute joint. Where? Revolute joint on the bars. Come on, no, please. No, don't do this. Don't do this. They will rotate about the z-axis, which is this one and this one. They will not even rotate about the x-axis. Oh my God, no! No, it's not correct. It's not admissible. It's not. Please, he changes the axis. Oh, please, yes. Let's make this the z-axis. Yes, maybe he will achieve. This should be the proper axis. Leave it like that. Come on. Yes. We kind of have something. Yes, it could be. It could be. It could be. Yes. Joint load. Yes. What? Ground to part body. So this is this one. Rotational velocity in transient. This is. It looks correct at this moment, because transient is time agnostic, so time is proper, and he will apply rotational velocity, which I cannot use in static. Rotational velocity, 100 radians per second. 100 radians per second divided by 2 pi. It will be a few dozens rotations per second, which is very, 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 it's It's very much for this scenario. Let's see what occurs here. We'll leave it like this. These are the default contacts. As I predicted, I think we'll need to, not here, but here we'll need to modify the contact properties, right? My opinion is that at this moment, it's kind of a small friction coefficient. If we're doubling it, we will have also a nicer solving. Let's go back to our colleague here. Rotational velocity. He changed from radians to rotation per minute. Almost 1,000 rotations per minute. Yes. Okay. Here is starting with this velocity. I hope you know what, I will do something like this. Maybe in order not to interfere with my webcam. Another joint load. No, please, no. Don't apply the, no. Joint load only on half a face. What? On, maybe it's a display convenience. Maybe the joint load is applied on all the balls. Why do you rotate the balls? In reality, no one is rotating the balls. 100 RPM. So he rotates the inner hub, then the balls, come on, no, please. Rotating the inner hub makes sense, but don't rotate the balls. The balls will, okay, come on, no, please don't do this. Fixed, he fixed the outer. Yeah, it makes sense if it's in a housing, yes. Let's look a little if we have a question. We have a question. I don't know if you can see it. Let's do something like this. Is there a way to generate mesh faster? Does it depend? Yes. So let's answer this question. Faster, and does it depend? Yes, sir. We have here, in principle, we have these things, number of CPUs. So if you want to make it faster, in principle, you can select number of cores here. Instead of program controls, you can click here and you select many physical cores. From my experience, it doesn't work. It doesn't make it faster. From my experience, I don't know about someone else. So normally this should be. Also, yeah, coarse mesh. Coarse mesh makes the meshing process faster. So number of cores here and coarse mesh. I leave it program controls because sincerely I don't see any difference. And yeah, I don't care anymore. Also, look here at the quality. In here, for smoothing, if you want faster meshing for smoothing, you can select here coarse. And also keep this the resolution very small, 2, yeah. If you go to 3, 4, 5, 7, 6, 7, whatever, then the meshing will be slower. Please don't make the mistake that many people make in the beginning and assign a very extraordinarily looking, professionally refined mesh, which will not lead to anything because it takes hours and days to solve something. Instead, go for a quick, I would not say dirty, for a quick meshing and kind of in the middle, not too coarse, not too refined as you see here, okay? And a very good thing to remember here, fast and coarse. This ensure a fast solving. If you change them to medium or fine, then it will take some time to solve. Yes, I thank you for the question. It's my first question during a live stream. So let's see if, yes. Where were we? Our colleague here was performing a simulation. He fixed the outer rays. Yes. What about my, I don't like how it evolves here. One, I don't like because it takes too much, and I don't like the trend. Okay. First thing, stop. It's not a problem with the analysis settings, with the time steps at this moment. It's clearly a problem with the contacts, I would say, from my experience. Okay, right-click, clear generated data. Yes. And here, at this moment, just for fun, let's change to 0.1. The usual friction coefficient between steel and steel is 0.1, 0.15, something like this. Let's also leave it program controlled. I think because we have 0.1, we can have such some rotation. Also, it does not help that we don't have a close contact. We have kind of a big gap. Yes. Remember, you have here what we call a solution information, right-click collection. Can we have like a generate or something? No. Come on. Create contact tool. In here, right-click, generate initial contact results. This is very useful for professional users because they have an idea about the gaps. What? Why? Come on, do it. Why don't you want to do? You have a contact tool with invalid contact selections or result requests. What? Oh. Insert initial information? Come on. I usually don't use this tool. You can understand that this is why I don't know why at this moment it does not work. Let's not stress too much on this. We remember there was some gap. Yes. And we can overlap that gap. You know what? Let's make like a section view. Something like this, okay? So you can guesstimate, if you have patience to zoom in as crazy, you can guesstimate, even though it's unprofessional, you can guesstimate like a gap, 0.02. So maybe we need to somehow decrease this gap, okay? We can resize the balls, but in principle, we might lose some of the contacts. All right. So Let's see what happens with the higher friction coefficient. Save solve. Then we can use what we call a pinball radius in order to allow the nodes to find them. These nodes to find the other nodes, yes, from the contact pairs. Let's solve. Let's like this with the higher friction coefficient, and let's see what happens. Back to our video. Fix support, analysis settings. This should be nice. He does it in one step, initial time step, 0.1, 0.01, 0.1. I don't know, because he has almost 1,000 rotations per minute and he's using such big time step. I have my doubts here. Direct, I like iterative instead of direct. Oh, okay. Yes, why not? Large deflection, please make it on. No, large deflection, no, please, no, not possible. Come on, this is a mechanism. You should have it on. No, please. Over progress. It's solving. Of course, it's solving because you already solved it in the past. The deformation is large compared to the model bounding box. Verify boundary contact. So this is based on a abrupt change. For good translation, let me read it correctly. Contact status has experienced an abrupt change. And of course, they flew away in the cosmos because you have no. What? He does not use the true scale. So this is the first sign of cheating. Okay, he uses a very microscopic scale because in reality everything flies away in the macrocosmos. So the usability, the reliability, the usefulness of this simulation is tangential to zero. Okay, so almost zero. I would not say zero because he had some ideas with meshing and a few of the joints. But oh my god, it's not. Look at the result scale. So you should not believe anything that you see. Oh no, please. It's at this moment it's not laughable, it's sad. Come on. Dude, what are you doing here? Come on. So we kind of yes, this is whew. Oh my god. Oh no, please. No, please. Fatigue failure of ball bearing. This should be interesting. Let's see what happens here. It's not nice. I would not say it's nice. All right. Any other question? Yes, we see some questions. Okay. Let's make it like this in order for you to. Nice contact definition. Thank you. I just wondering if the case was validated. No, because I just made it. If you go towards the beginning of the stream, it's a model that I just made it from zero. So come on, it's for tutorial purposes. For this particular bearing simulation, is it possible to get results about the heat generated from the spinning? Is there a way to do that? This is a very nice question. And yes, there are ways, but this is pretty complex. In order not to let's say, to prove that I'm not bullshitting you, I will say you at least, I would show you at least one way. Let's look here. I have made a while ago this thing. This is kind of the easiest way to see the dissipated heat. All right, and this is kind of the easiest way. But there is another more thorough way and very nice way. So the clip is called, can I move this? Okay. The clip is called heat dissipation in a shell bearing with the high friction coefficient. I said the high friction coefficient in order to dissipate more heat, okay? I use the shell bearing because the solving took too much time and I wanted a very coarse mesh with very small amount of nodes and very small, let's say, degrees of freedom to calculate. This is why I used something like this, not solid. Let's look about the heat dissipation. So it's by the way here time makes sense because it's explicit dynamics. When we're talking about dynamics, we're talking about time. Yes. Look here how large the gap is because the cage is designed only to kind of hold the balls. Okay, they should not restrict the balls. There are some small holes for the Kim, the one that is a knowledgeable person. There are small balls because otherwise I couldn't have make a shell out of a sphere. In space claim, you cannot make an empty shell sphere because it will automatically make it solid. It will fill it up. And in a few seconds, we should see the temperature. Come on. This is the stress. I will fast forward. Vectors, very cute. Of course, because it's made by explicit.com, by me. Okay, so. By the way, it rotates. We don't have bonded contacts or no separation contacts. Why it rotates? Well, you know what I rotated here? Here I rotated the cage. And I left the other things, left them fixed, I think. Yes, and I rotated the cage. Even though it's not real, yeah, it's not realistic, but I wanted to rotate the balls. I think you can understand the purpose of this. Where is the heat? This is the heat, yes? So remember, due to friction, we have heat generated. This temperature all, it's not default. It's not default. Yeah, in explicit dynamics. So my dear Hassan, I think I will say Siti Hassan. You will access the temperature from here. This, after the solving is finished, this worksheet button will be open, will be active, and you can click it and you can find almost at the bottom, there will be a list. You can find temperature all in explicit dynamics, not here. In static structural, there is a temperature, it's called BFE. BFE. It's called in static structure, but it's pretty complex to. So I would say at this moment, in a simple manner, for a beginner, it's not easy to dissipate heat. The easiest is in explicit dynamics, okay? And remember, you can access the, again, you can access the temperature all item from this button, from the worksheet button, after the solving is made in explicit dynamics, not here, okay? I can maybe show you the temperature all. Temperature all temperature, all ANSYS images. Does anyone show it? No. Why should they show it? But it says the term temperature is a specific user-defined result. It's used in a specific, exactly what I told. Result retrieval, source of heat, blah blah blah. Remember always to ask Google, ask AI, ask, and they will help you. They will help you very much. Maybe you can ask here, hey Claudio, why isn't heat dissipated towards the races? Yeah, if you move the threshold to maybe 10 or 5 degrees above the room temperature, let's say 25, maybe you can also see the heat in the races, but it surely is heat dissipated in the races. And the other solution, which is the nicest one, and I think I will make it in the near future. It's not very easy. It's this one. So look here. A very easy way to simulate heat dissipation is using coupled field, transient or static. There are many coupled field simulations. Let's go here. Maybe we can see them. Couple. Look here. Couple field harmonic model, static, transient. Yes. If you use these, then the exchange, the correlation, let's say, between a pure mechanical and like a thermal FEA, then it's easier to simulate. And so this is what I have done, okay, in coupled field transient. So I'm pressing here, the brake pads press this disk gradually in time. In time, because it's transient, time has sense here. And look how it hits the disk, the brake disk. Okay, let's go for we have a heat flux, by the way. Let's go for the temperature. Look here at the temperature. Yes, it looks very nice. I need to make it full screen because it's so nice. And I worked so much on this. So much I worked. Oh my God. Yeah, let's do it again. Maybe even play it with the lower. Okay. And it takes into account these separation walls. It's so nice. The separation walls, with in reality they act like dissipating, heat dissipating fins. Yeah. This is a forced reaction. So this is the second way. So as I told you in the beginning, this is the beginner way, the kids way, let's say, and this is the more, let's say, professional way, using ANSYS coupled field transient. And yes, I have the simulation. Anytime you can download it, take it, and you will see what boundary conditions I have used there. And in the near future, I will begin and make a live streaming with this gradually, because the FEA is pretty complex. I'm not running from difficult simulations, from complex simulations. Instead, what you need to understand is that in a live stream, everyone wants results. If we are just talking and we're just solving, look here, this is solving. If we're just solving and no result appears, everyone will be bored and they will question your expertise. my expertise in this case, yes. So this is why I need to begin with simpler cases in order to gain, for my audience, for my spectators to gain trust in me, even though I have more than 400, I don't know, 400 something simulations made. I need to gain the trust of anyone and everyone that is watching me. As long as we are here, I don't like how it goes. This means that the gap is too much. I'm talking about the gap between the balls and the races. It's too big allowance, let's say. Clear generated data. All right. Maybe a very easy workaround, maybe, let's see, is to make here just a touch. Let's see if it forces a touching of the faces, of the mating faces. Let's see if it works. If not, we're going to go for the pinball region. But let's see at this moment. Also, let's make it even cooler. Because I want even quicker solving. Can we reach 100,000 nodes? Let's see. Yes, almost 100,000. You can scream, no problem. Hey, Claudio, what is this? But believe me, this is how a beginning should. This is how a start should look like. Yeah, quicker and faster. Let's say scenarios, iterations. Save, solve. Let's see if it works. So thank you for the questions. There is an unanswered question here. Thanks for live stream. We'll check the full contact later. Yes. Can I reply on the hide user at this moment? Channel to go to channel. So let's try and answer in writing. Let's do something like this. Is there a way nice contact thanks, just modeled it from scratch, so no validation today. No validation today. And let's, is it possible to get results at city? Yes, explicit or coupled field. See my simulations. Search expert FEA wearing heat. Then break heat explicit FEA. Then is written like this. Yes, we kind of answered. Simulate the vibration under. Yes, anyone and everyone wants to do it. Simulate the vibration of a ball bearing under running condition and under different speed, load, and it's easy to say. It's easier said than done. I will write something. I'm sorry for the abbreviation. I don't feel like writing all the words, the entire name. Sorry. Very complex, needs computing clusters, etc. And I will explain. So, dear Prashant Jain, okay, we are simulating 100 degrees rotation. This is 30%, less than 30% of one rotation. And you suggest, and it's normal to suggest, it's no problem to suggest. You suggest to simulate the vibration of ball bearing under running conditions after hundreds and thousands and millions rotations. One, you need a very powerful cluster, cloud, HPC, whatever computer system from a university or, I don't know, company. And two, the easiest way is to use some system simulations. I'm talking about something like 1D simulations, something like Simulink, where you treat these problems from an overview. What we are analyzing here, to analyze means to go in depth. What we're analyzing here is, let's say, more in detail. But more in details means shorter portions of movement, shorter durations, smaller geometries, smaller zones. It's like we are going towards, I would not say microscopic, we're going from macroscopic to smaller. What you need to, in order to increase the time, the loadings, the rotations, all these conditions that appear after many hundreds hours of operations, you need to enlarge the scope. You need to go on a macroscopic level, and this is very, let's say, reliable, made in system simulations, in 1D simulation. I'm not expert in these simulations, but maybe I will show you like what is about. Look here. Is a fast system level modeling technique that analyzes physical behavior, fluids, heat mechanics. You understand? So it does not go in depth. You don't make a CFD, you don't make a thermal, you don't make a static structure simulation, but they are idealized, they are simplified. Look here, for this turbofan, this is not so cute. Maybe here it's nicer. Yes, you idealize and you simplify. You work almost with symbols. Yes, and this is what you need to have to achieve such a complex simulation. You can, of course, at this level that we are now and today, and with our computer. Yes, you have maybe a laptop. I have workstation here, we have, I don't know, 4 cores, 8 cores, 64 cores, whatever. We need such complex simulations as you propose, Prashanti. It's yeah, it's very complex. Sorry. So let's yeah, and it takes lots of time and expertise, of course. Why I feel that something is wrong? Yeah, something is wrong because I don't hear the fans of my computer. Just remember, when we are solving with 50 cores, then the fans go a little crazier, and I don't hear the fans working. It's clear that something stopped here. Let's clear generated data. Yes. Solve and maybe solve it again. Save, then solve it again. By the way, thank you for the questions. Pertinent, good questions, and yes, thank you. And I understand you, students, master students, PhD students. I understand your question because your questions come from your advisors, from your master class advisor, from your PhD advisors, and they want these made. But no, such simulations, they need to be correlated with what we see in laboratories and in real life and in the plants. And yeah, so at this moment, today, and in this live stream, we're not there. Solve. All right, I wanted since a while ago, since yesterday, I wanted to give you a small tidbit, advice, something. I want a blank screen. This is a blank screen. I want to give you some advice on this thing. In principle, in FEA, to make something work, you need to discretize. And I will make something like this in order to easily be seen after the stream ends. For a second, I will check my smartphone. I have a small an SMS to answer. Please excuse me for a few seconds, please. Yes, I answered it. I've seen it. I didn't answer it. Okay. Where were we? Here. Yeah. All right. We'll talk about FEA discretization. What I mean. If we have the patience to discretize everything, in principle, we should be golden. We should solve anything and everything. In principle, if the model is somehow correct. I'm talking about the geometry and the materials and the loading conditions. If they are correct, applying discretization at all levels, it should work. Let me tell you what discretization means. We can talk about connections. This means, I'll write here, connection. On the connection level. This means refine meshing contacts, let's say. contacts. This is a form of discretization. It's like a physical discretization. Okay? So, define mesh and contacts in order to have more contact elements, something like this. Okay? I will not insist at this moment on this type of discretization. Let's go to the one that anyone has heard about, mesh level. This means refinement. Refine mesh where needed, by the way, where needed. Don't refine everything. Sorry for my writing, but it's with the mouse. This is easy to understand, right? There is another discretization. Yeah, we're following. Connection mesh, there is this discretization. Regarding analysis settings, I'm talking about the number of steps. There is this discretization. It's like a solver discretization. I will write here in order for you to remember it. This is A, analysis settings. Settings. How do you write S? Settings. I'm talking about, I will not say refine, let's say decrease. Decrease time steps. Time step values, okay? In general, we'll say time steps. And for this one, related to boundary conditions, okay? To loads. For will be and is I will say gradually apply loads. Yeah, gradually. If you have a number, split it in 4, in 10, or something, yes? So, I will write this, not 0 and 360 degrees rotation. I will make it like this. Instead, go with 0, I don't know. Yeah, 60 degrees steps, okay? I'll not write this as symbol now. I don't feel like doing this. I'll do it in the end, yes? The degree sign. This one. This is a proper discretization. Remember this golden rule. Discretize everything. Yeah? There is a saying, there is a saying, let me write this down, this saying that I've heard maybe 2 set violin, this channel, maybe I've heard it first there. The saying is like this. If, I will paraphrase, I don't know if it's the exact saying. If you can do it faster, you can do it slower. I'm talking about FEA at this moment, okay? No wink, no smile, okay? No emoticons. Slower. So my advice is not to force things, not to go very fast, but to gradually increase the mesh. Yes, this is why here I said start with coarse. Start coarse. Okay, and this start coarse, it applies also to kind of anything and everything. Then you can refine. No problem. This is what we have done and what I'm doing now. Does it work? It does not seem to work. Come on, why are you? Why are you not cooperating? Why? All right, with the just to touch, it does not work. We have very big. We have too much gap, okay, between the balls and the other parts. Do you have something else? Thank you very much. You are welcome. Or in my broken Hindi, I will say Dhanyavad, even though I think we have an additional. No, it's good. It's correct. I don't know how to say you're welcome in Hindi, so let's leave it like this. Clear generated data, yes. Where are we? How long do we avoid the decreasing the gap? How long? Let's try with pinball, then we'll modify the geometry. No, just we go default or add offset effects. Pinball region. Let's go for auto detection there. Yes. So you see it kind of feels the value. Yes. This is from the meshing. I don't think it's real. Okay. Let's solve with this. I would like to point out something very important. The difference between static transient, this package static transient, and explicit dynamics. The difference is this one. In static and transient structure, you can modify and bend things almost towards absurdity and towards cheating in order to make the solving work. You can falsify, let's say, the geometry, the mesh. You can kind of falsify using these properties. These are kind of theoretical ways and means to kind of falsify the reality, because it will automatically move something. It will move a face, it will move a node, it will move a surface, it will inside the solver. Yes, it will not use the real topology of the geometry or the reality of the mesh sometimes. In explicit dynamics, you can no longer do this. You have an offset, which is like a pinball in the contacts of explicit dynamics. You can no longer do this. Explicit dynamics in many ways is the most realistic simulation. I'm talking about what you see is what you use, what you get, what you simulate. This is what explicit dynamics does. This is why explicit dynamics is preferable also by lots of beginners, okay, also including myself, after 20-something years of, maybe 20, 25 years of ANSYS work. Where I was pointing is here, it can be kind of forgiving in static and transient. If you do some things wrong or the topology is not correct, maybe you can somehow adjust it with these settings and values, but not in explicit dynamics. Explicit dynamics is based on reality which is the topology of the geometry, the real shape, let's say, of the geometry, and the real location of the nodes. You need to take this into account. If you don't understand it now, you'll understand it in the future when you encounter what I was talking about. Let's see if the pinball radius did something. So until now, what you have seen my struggle to adjust the contact parameter, faces of detection, to adjust it only theoretically, let's say, in the solver, in the program, because my contact is lacking. I mean, my contact has, here it looks nice, but it has, for example, here it has too much gap. All right. I'm showing you all these in order for you also to traverse all these milestones and to see the possible solutions, the possible ways to alleviate some problems. Okay. Yeah, it does not look too nice, but it looks nicer than before. Where are we? Here. Let's go. We were enjoying some interest. Here. All right. Ball bearing, fatigue failure. I can predict it. I can already predict it. I can already predict that there will be a fixed ball bearing, and he will access the fatigue tool, because in static and recently in transient you can access a fatigue tool, very simple fatigue tool. And yeah, I think there will be no rotation. This is my why am I right? There is no rotation. And if you make a ball bearing, if you simulate a ball bearing, it's from 0. So if you make a ball bearing not rotate, it's not a ball bearing. It's a dead part. Okay. He put a coordinate system in the middle. Why? We have contact regions. No separation. Everyone is no separation. It's clearly that someone copied someone. Everyone copied this or another person. Separation. He's fixing the yeah, it's a repeat of what we have seen in the past. It's useless. A displacement on, yeah, it's what we have seen it in the past. What he has done, he noticed that there is a fatigue tool. By the way, he's showing that there are fatigue parameters in the steel. He's showing this, yes, they are default. And look here, this is somewhere there is this tool. He's not showing. In the solution tab, there is the fatigue tool. And you can see that, let's say it does not there is a safety factor and it's less than 1, so it cracks, it breaks. Life, 69,000 cycles of load, and yeah, you have a fatigue and no rotation. You have, yes, it's yeah, it's, I have no words. By the way, if we want to laugh a little, let's see my first ball bearing FEA. This should be interesting. Oh my God, I feel ashamed. Oh my God, it's so awful. Oh, but I had the decency of saying trial. My colleagues from before, a few minutes ago, they didn't say trial. So, oh my God. Until I guessed the proper contact properties, oh my God, it took so many trials and errors, so many sleepless nights. Oh my God. Oh, yeah, we all have a beginning. Oh no, please, no. Why? What is this? Please, dear Indian colleagues, please don't show this. No. Just keep it on your computer, delete it. No, don't publish this, please. Don't take it personally, my Indian colleagues, please. I've seen Indian names, so yeah, so please don't take it personally. If you have something that does not work, Keval Kona, this is Indian name. If you have something that does not work, don't publish, don't keep it for yourself. Look here, something like a Russian engineer, Dmitry Yatskovsky, I think. Let's see. Slavic origin, I don't know, Russian, Ukrainian, something. It rotates nicely, and where are the balls? Hey, where are the balls? Please. Yeah. This is masterclass. This is how it should be done with a proper cage. Yeah. Look here. This is so nice. Yeah, this is like Nirvana. Господи Dmitry Yatskovsky. Look how nice. And he has a very fine mesh. It took so much time to solve it. You know, yeah, maybe you already know it by now. You can refine you can move the threshold to have more colors, let's say, okay? So yeah, it looks very nice. Look here how the contact is propagated. Oh, we have a ball. Yeah, it's not important, but yeah, this is a masterclass. Test for bearing radial force. I think it will just compress it. Let's see his channel. A sync, yeah. Ne opozdaj krotkometražni film. Yes, I will not enter into detail. Another guy that I respect very much is this engineer. I think he's Japanese, I think, and he's on another level, on a different level. I think he is mastering everything that is heat source moving, heat dissipation, laser welding. So I think he's more than, he finished his PhD, I think, recently. And yes, I think he made his PhD in Germany. And yeah, Franz Kefuka, Mr. Franz Kefuka, very, very knowledgeable dude. Also, other guys, I will talk about them in the next streams. Let's see if we have something. No. All right, let's not waste any more time. You know why I was avoiding modifying the geometry? I was avoiding it because it usually updates the contacts and kind of ruins the contacts and the boundary conditions. This is my experience from the past, all right? So let's duplicate this because we have something, okay? Do we have any question in the stream? Okay. 1D simulation. Yes. Well, whoever is interested, she can go and meditate more on that topic about system simulations. I call it this. I call it template, then duplicate. Couple, yes. Yes, we'll take a look also on my simulations on bearings. These are cute. This should be interesting. Where are we here? Let's kind of minimize a little to minimize the white zone. Double click and let's decrease the gaps. Let's make these opaque and check the gaps. We can measure these gaps. Measure. I will click one edge, and with Control pressed, I will click the second edge. So look here, 0.015. On diameter? No, on radius, 0.015, and here 0.015. Oh my God, it's so precise. And I made it ad hoc on the spot. All right. Let's increase the ball radius. .54. 3.55. Undo. 3.547. Oh yes. Oh yes. And you remember? 547. Okay, everything is good. Remember to always check the interference. There are no interfering bodies in the model. Okay. Everything is nice. Let's leave it open in order to have a faster loading. Yes, you've seen how fast it loaded. So it does not change anything above contacts. Let's go for contacts. What? So forgiving. Thank you very much. Thank you. The contacts are not ruined. Thank you very much. Thank you. So I was afraid out of nothing, without any reason. Let's go here and make it default program controlled. And let's run it without anything more. Mesh. Is the mesh good? Yes, yes, yes. Also, a thing that I kind of forgot, I should have decreased the loads, let's say. I kind of forgot. So instead of 25, let's make it 50. You know what? Let's run it like this to see each echo, the answer of each change separately. Okay. Save solve. Usually, when we update the geometry, ANSYS inserts a new bonded contacts. Usually, so always check these and the boundary conditions. Yes, look here, look here. It inserted fixed boundary conditions. We select them, delete, yes. Yes, just, yeah, I was right. So pay attention when updating the geometry. Solve. Clear generated data, solve. Clear generated data, solve. Clear generated data, solve. We need copious amounts of patience, because if we don't have any patience, who is going to have patience? Yes, if I don't have patience here, will ANSYS, will the software have patience? No. I am forced to have patience. To rerun, resolve, regen, clear, submit to solve. It begins to look nice. Yeah. So where were we? Here on the bearing, I would like to see this, because it looks very nice from at the first glance. It looks very nice. Ooh, yes, yes. This properly made simulation. Does he have more? An abacus, of course. Abacus and where is ANSYS? Come on, here is ANSYS. It's, yeah, it's It's correct. It's I like it. Where is ANSYS? Where is ANSYS? Mix pocket differential there. Yeah, he has done lots of FEA, lots of FEA. This is ANSYS. Oh, yes, nice. I think it's it's rigid dynamics. Yeah. These are things that we'll do in the future streams. This is my version of the needle bearing. Force reaction. This is a section view. The section views in ANSYS, they are pretty weird when we're talking about rotation. Contact forces, I think. Strain, yeah, it looks very nice. I like it. Let's see something in LS Dyna. This is the one of the ANSYS partners or distributors, ANSYS dealers in Romania. I know this because I am from Romania. So what I wanted for the playback to be slower, because I want to see the balls or the rollers rotate. It's balls, and they seem to rotate. Yes, of course. Judging from the contact patches, the balls rotate. Yeah, very nice. And very thorough simulation. I'm talking about the mesh sizing. Come on, it's super professional mesh sizing. Yeah. Roller misses again. What? I don't think it's FEA. I will not go there. This is something very, very interesting that I've done a while ago, 1 year ago. This kind of shows and explains the principles of a roller bearing, let's say. Yes, it looks simple and easy. It's not so simple and easy, but yeah, it's very nice. Let's see here. We have something. We have something. Yeah. SKF taper instead of tapered. Tapered or tapered? How it's correct? Tapered. Okay. All right. If you contest my, I don't know, my need for proper spell check and grammar, please take into account that we all have international colleagues, and it's of utmost important to have the cleanest language and spelling and expression. So please have a very good fluency expression in your international language, because this will open many doors for you, for everyone. So he imported a roller bearing he's meshing, but what about the contacts? Come on, contacts. Why? What? So this means he left the contacts bonded. Please don't do this. Please don't leave the contacts bonded. Please. All right, so where were we here? Please don't. And the mesh is a messy mix of hex and tetrahedron. He fixed the outer, and he's, come on, he's applying a pressure. So he's, who needs this? In reality, there is no bonded. No, come on, please, no, please. Finally, we have a crash here. Yes, ladies and gentlemen, this is the, yeah, this is what we have to fight until we, you understand now, if we had the contacts bonded, we wouldn't have this. This we have when we have nonlinear contacts, and we have to make a trial and error. All right, let's dust ourselves up, and let's switch from default. Let's go here to asymmetric formulation, augmented Lagrange. Normal stiffness factor 0.1, update stiffness each iteration. Let's run it like this and see what happens. All right. Maybe you are asking yourself, hey, Claudio, why do you criticize the FEA of beginners? If you are an absolute beginner, include the word trial or attempt, not finished, and converge or something like this, okay? Or please don't publish, don't, because it gives no value. Look here, a bearing that does not move, it does not do anything. Disk rotation using structure, it rotates the disk, but yeah, nothing happens here. This is a nice try. It rotates for 1 degree or something. My assumption is so my opinion, at least myself, I don't publish something that is not worth, or if I publish something that it's not so very useful, I'm writing the word trial or something like this. But yeah. Let's see. Welcome to FEA simulation. it's very promising. It's very promising to get help with their simulation. It's very promising. A small problem would be that this mesh is very coarse. It should be fine, and maybe it will work more. Yes, it's promising. Port Said University. Why do you write cities with small characters? It's not normal. You should use caps lock. Mr. Mohammed, let's see what you share with us. Stress analysis for deep groove ball bearings using finite element analysis method. The English is very nice. Dimensions. So, what? Oh my God, it's so nice. Look, this is something that should be shared. This is a plus value. We need to aspire to do something similar. This is very cute. Yes. If he would have decreased the threshold, just dragging to, I don't know, 700, 500 megapascals, we would have seen nicer colors and maybe a little finer mesh. A little finer mesh. Not too much, but a little. You see a coarse mesh and the ball bearing works very nice. Maybe you ask yourself, hey Claudio, why is he showing a nice simulation and you are not showing a nice simulation today? So my reply is hold your horses, and you don't know how many weeks took this, and also what you don't know is how many customers purchased my simulations. And after they purchased my simulations and tutorials, they began and publish such simulations. If you will go and see my simulations, in general, after I publish some simulation, in 2-3 years, then others begin to copy it. Believe me, you can check it. Nevertheless, this simulation looks very nice, and it was very hard to do it. It's very complex, as you can see in the present stream. Spherical roller bearing. Come on. What is this? All right, the other refinement that I mentioned the other refinement was here, 15 and 60. So what you see now is a bearing that I modeled. I didn't see it until today. I just modeled it from scratch. So yeah, it's not previously exercised, yes. I'm trying to find excuses for my loss of convergence, but yeah, with patience we will solve it. Why so fast? Why are you in a hurry? Final project, failure analysis of spherical roller bearing in roller tables of continuous casting machine. This is KKK spherical roller continuous. Dosian, it looks like something Southeast Asia, maybe Malaysia, Indonesia, something. It's written here. Polytechnic pe manufacturing in Oh, dude, you don't fool me. Let me show you what you have made there. We might need to increase the frictional value a little. Look, no. These are bonded. The rollers are bonded to the races. This is why they behave like this. They don't move spherically. How can you see? I would like to show it to you. Look here. These rollers are buried. In the cage, they are not properly displaced. This is why they don't show the legend. Okay, maybe we see it here. They show some legend. They don't show the scale. They don't say anything about the contacts. What? No, it's not. It's not correct. No, it's not. No, dude, you don't fool me with this. Okay. Right. Where are we going with this? Nowhere. All right. Let's achieve results because the time passes by. Do we have any question? Thank you. No question. Okay. Clear generating data. Yes. 0.2 is kind of a limit, so let's use 0.19. In ANSYS, there is like a threshold regarding 0.2. Does it work? All right. Come on. I am almost at the point where I think I will suppress half of the balls. And run with fewer balls just to make the FEA solve. All right, where are we here? Oh, Sufyan, I know Sufyan. He's a nice guy, and yeah, he has knowledge. Yes, he has done something nice. Sufyan Ahmad, yes, this is a nice FEA. Look, with the quartz mesh, and it still works. Yes, he understood the principle. Nice FEA. ANSYS meshing. What is this? Gear spline rotation? Mr. Ufuk, let's see. Kortac, he seems like a Turkish. Defective bearing analysis. Stress and vibration analysis of rolling element bearing using finite element simulation. Bearing. It looks nice at the first glance. It rotates correct. Yeah, it rotates correctly. It's nice. This is a nice FEA to publish and to show. This is plus value. Yes. He has a defect. Hole, and yeah, there are some jumps. And something. I think this is acceleration on y-axis. I think. It might be acceleration. Yeah, nice FEA. So, contact stiffness. Yes, this is. We will treat this. We will discuss about this in the next streams. Pedestal bearing. Oh, do we see something here? Let's see. Application of bearing load. It's just a load. It's a bearing load, yes. Spur fatigue. This should be cute. Does it rotate? I will not divagate too much because I will make a live stream with gears in the near future, so I will not digress too much. You need the bearing which one? Remarks, yes. Does this work? If this works, then yes, my respects. It works. It looks very nice. It's I think it's rigid dynamics, I think. Yeah, it's very nice. Pretty simple, simplistic, and nice. Does it have something more? He has something more. Ooh, deep drawing. Rule forming. Let's see. ANSYS mechanical. Oh. Nothing happens. So this is 0. Deep drawing. Yes. Yeah, this works. And did he do it? No, he didn't do it. What? Yeah, he made, let's say, the beginning of the simulation. It's a nice trial. It's not finished, but it's a nice trial. He's on the right path. Analysis of pedestal. All right. So where are we here? I don't like it. I don't like it. All right. Go to inner. What to do in order not to damage the simulation too much? In order to keep a shred of common sense. Ladies and gentlemen, do we go for adjust to touch? Do we go? Yes, let's do it. Clear generated data, yes. So I'm looking for other people's simulations also for me to learn some things where possible. So he has materials and come on. Come on. When this value, the initial value, is so high, then it's so high compared to this value, then yeah. This is the criterion, which is too small comparing to the force convergence value. You can also read all these here. Force convergence value and the criterion. Look here, these two values. When they are so far away, it's not nice. When they're too far apart, it's not nice. All right, where are we? Here. So he's inserting a pressure. By the way, he didn't interfere with the contacts. This means the contacts are bonded. He fixed something. He's putting a pressure like this. 30 pascals. It's too little. It's nothing. 30 pascals is nothing. .30 pascals is nothing. He exaggerated the scale. Look at the displacement. It's close to Planck, to the Planck limit. Oh my God. It's less than nanometer. Pico. 0.2 picometers. Oh my God. Attometers, I'm sorry. 0.2 attometers. From a pressure of 10 pascals, not megapascals, not. Oh my God. Yeah, nothing to learn there. Mr. Meric, I think, Buyukuyunku, I think he's Turkish. Oh, he's done the same thing as I'm doing. Normally, I'm doing the same thing that he's doing. What language? English. The quality is very nice. I think because he uses a smaller resolution. My resolution from my computer is 4K, and I think he uses 1080p full HD. Nicely explained, yes, very nice. I'll subscribe to this colleague. Yes. Very nicely explained. I'd like to see something more. I mean, something more complex. Yeah. Gain an audience with mechanisms, with explicit dynamics, with crushes, with, yeah, so, but yeah, 2,000 subscribers. It's nice. So he does a very nice job explaining also with the theory. Yeah, it's nice. Learn ANSYS in 10 days. Wow, this is something to remember. In 10 days. Oh my God, and I'm struggling for more than 20 years. People nowadays can evolve so much faster. Let's see if this decreases. I would like here to see what happens because it's in SolidWorks, and normally it should not work because we don't have high nonlinearities here. What is this? It's like a pressure from the outside, no cage. Fixed inside and pressure from the outside. Oh my God. What? Force, which is pressure, yes. Come on. No, please. No, we can do this We cannot do this in a SolidWorks simulation because it's very limited. Cute but no cigar, as we usually say it. This should look pretty nice, but I think the reality will not be. Carry, come on, I write correctly. Your carriage, it's not correct. We'll soon make gears, meshing gear simulations. I'm talking about live streams. Yeah, I still don't like what's happening here. All right. Why doesn't it work? Why doesn't it work? Why? Let's force something, you know? Let's go again to 25 and 100. And let's force a convergence. How do we force convergence? Look here. I select all the steps, nonlinear controls, and stabilization. Save and solve. What is my problem here? My problem is that I don't want to wait more than 15 minutes to have results, more than 30 minutes. I want to obtain results quickly in order to have solvable FEA during this live stream. What you see on the entire YouTube, it's the results of days and weeks of solving. I am constricted, let's say, restrained by time. So yeah, this is why you also gain lots of knowledge and, let's say, workarounds and tricks in order to gain a quick solving. All right. Bearing, can we see some bearing in LS Dyna? Oh. Bearing plus bullet, why do you have, would you have bullet in LS in a bearing? We don't know. Ball bearing simulation. All right, so where were we? Here, not so nice. I will see this if it converges or not. So what is this? I don't see the balls moving. So something is not right here. The balls don't move. The entire assembly seems to rotate, but the balls don't rotate. This is why he's not showing more. No. A bullet destroying a bearing. Yes. Interesting. In 3 years he has no like. Should we give it a like? Maybe another time. They rotate. He put a small patch to show the rotation. Yes, nice. Workbench simulation too. It's a tongue. He looks like maybe Thailand or Vietnam. Does he have more? Oh. Oh. Mr. Tang, you have complex geometries here. Oh my god. Oh my god. Oh my god. So nice. Oh, finally someone who has something to show. This I need to say. Clamp for triangular objects. Oh my god. Oh, this is poetry. Mechanism poetry. Mr. Feng, I think you gained my subscription because I'm interested to see so many beautiful things. Albeit, yes, mechanisms. Mr. Thing. Let me go back. I'd like to subscribe, yes. What software is this? Motion Solve. This means we have, I think we have rigid dynamics. Oh my god. Will it converge today? Ah, I forgot to activate for the first step. Oh my god. We have 3 hours of streaming. Clear generated data. Yes, let's activate for the first sub-step. Yes. It should work. Come on, it will work. Clear generated data. Yes. Solve. Do you have any question? No. Ooh, nice. It started immediately. The value increased so much. Okay, we will see. It seems to rotate the balls. Yes, it's pretty nice. So in my books, this is and it's closer to reality because there is not much friction between the ball and the races, and yeah, it rotates once in a while because it's a very small friction coefficient. Mr. Pigan, what does he have more? Did he do it? Because it's yes, he did it. It's a very complex shape, and it's not easy to use it. Oh, very nice, very nice. Very nice, yes. In my opinion, Abacus is a little harder to learn and to master, yes. While ANSYS workbench is very appealing and very... So with stabilization, finally, we are on the right track. We have our first convergence and 3 hours of live streaming. So complex. What is here? What do we have? This, how the bearings work? First in the world, yes, I know. Me, myself, and Irene. So after this simulation, many people published simulations after this simulation. Because there was a pioneer, okay? What is this? Bearing with DEM, what? This is the first time I hear. Well, this is sad. This is laughable. Yeah, so if you fix the races and model, you solve. You don't put any load. Almost zero usefulness. Almost zero usefulness. So finally things are turning around. Same videos. Yes, 2 years ago, yeah. Nobody was publishing bearing simulations 12 years ago. ANSYS workbench. And this is now. 2 people watching. Me, myself, and Irene. All right. First time when I see done in DEM, we know it's a discrete element method, I think, DEM. And yeah, particles. Made with particles. What I don't see, so let me understand. The ball bearings touch the races, and the big balls, sorry for the expression, they touch the races, and the small balls touch these I don't know, lamellas, cage, this cage, and they seem to rotate. It's very nice. It's first time when I see something like this. It's very cute. Do we have something more? Dynamic ball bearing. Mr. Charles, I think. Présentation de la société également. Green Asset Life Cycle Monitoring Online System. Ah, and it was a while ago. He didn't recently. Roulement habile avec défaut sur une face lisse par la MED, which is the méthode des éléments discrets, je crois. So what do we have here? Oh my god, it looks so nice. I don't know what software is, but it looks so nice. What is the software? Modélisation dynamique d'enroulement 6208 2D avec la méthode des éléments discrets. La répartition de changements mécaniques au cours du temps connaît des sursauts, peaks, I think, causés par le défaut d'écaillage, by the defect in the, I think this is the race. Defects in race. Ah, yes, because here he has some roughness, and these rough surfaces, they kind of simulate defects in the races. Yeah, pretty cute. You have earned the like, Mr. Charles. Monsieur Charles. What? Come on. When you have the impression that something works, they hide it. But the mesh is very professional. Look here. The ball collides with the race, so this is not correct. The ball collides with the spring, leaf spring, whatever spring. The ball exited the race. So it's, yeah, this is why it's very short, 1 second, because zero usefulness, you see? The balls get out of the ball bearing. What is this? What? It's not normal, it's not correct, it's not almost, as I said, almost said. As I said, almost said. We're making word jokes now. How do ball bearings work? Let me tell you. They rotate, or at least some parts. The hidden complexity of ball bearings. I like this image, it's very cute. Stress and vibration. Ah, I've seen it. Finally, we're on the right path. I will not leave it until the end because I want to save time. Yes. Yeah, it works, ladies and gentlemen. With emotions, with some emotions, you know what? Let's make the mesh more coarse. I want a faster solving. .9, 0.9. All right. All right, and here I would like to have a little bigger friction coefficient. Who is propagating the friction? The inner. The inner rotates. So for the inner contacts, I would like to increase to 0.3. For the outer, let's leave it like this. Yes, and additionally, we have just a touch. All right, save. Can I make it 20 towards 80? Yes. So, to explain, I increased here the friction coefficient in order to have a higher pushing force, a higher friction force, which will rotate the ball, which will also be rotated by this friction force. We will see together. We will see. As I told you about this warning about the 0.2 limit, one or more contact pairs are detected with a friction value greater than 0.2. If convergence problems arise, switching to an unsymmetric Newton-Raphson method option may aid in convergence. Yes, unsymmetric Newton-Raphson, yes, maybe we should have used it, which is here, Newton-Raphson option. Let's hope it will switch itself. Nicer value. Convergence, this is what we need, this is what we want. Do we have any question from the audience? No question, okay. Perfect. This is the converging, the solving is the hidden part of what you see on YouTube. Nobody shows the converging for a properly defined simulation, because the converging takes hours, days, weeks. So yeah, it's a lot of effort. Where were we? Bearings. Oh, let me show you this bearing. Look here. So a while ago, maybe 3 years ago, I thought to myself, hey, why don't we lubricate this bearing? And yes, it was a lot of work, and it looks very nice. Look how the water is being drawn up by the bearing, is being pushed. And yeah, it looks so nice. And it's so much work. Oh my God, so much work. A thing that I would like to answer a question that nobody asked in this live stream. Someone asked about simulating heat dissipation. I have shown that I have simulated heat dissipation in explicit dynamics using shell bodies. In explicit dynamics, at this moment in ANSYS workbench, and since many years ago, we cannot have heated parts being cooled by a fluid. So, for example, due to friction, we have temperature, but this temperature will not decrease because of the surround fluid. Hopefully, cooler liquid. Okay. So I don't know if you'll see if I'm showing temperature. Maybe I will not show because it's not useful. Yeah, it's not useful, and it has also the problem with showing also negative values for temperatures, which is abnormal, and it doesn't make sense. So to answer a question, it's not in ANSYS workbench explicit dynamics. At this moment, I don't see how we can simulate the cooling of an assembly being heated due to heat dissipation, which occurs during frictional movement. Yes, bearings. Bearing cages. Other simulation? No. Bearing, should we go to this line or not? Maybe not at this moment. Come on, show me. Show me. Ah, it doesn't show. Show me intermediate results, come on. Oh, we have something. We begin to have something, yes. With the respective emotions. Big gap, big allowance, there are vibrations, yes. Ah, it's also explicit, yes. There is a fruit fly hanging around and disturbing the live stream. Unhealthy bearing simulation. Which is unhealthy, the simulation or the bearing? The ball does not rotate. Oh my God, why? Incorrect boundary conditions. Come on, come on. What software is this? Something in this made by Siemens. Where are we here? Let's decrease. Oh my God. I don't know. Oops. Section. It looks kind of awful. I will admit it. It looks kind of awful. All right, unhealthy. Look here at the interface. So, oh my God, output, model, spectrums, plots, paths. It's not user-friendly. Tell you what happens. This person kind of fixed the rollers, and he rotated a sub-assembly because I don't see the rollers moving. Does he have a laser forming? Yes, sir. So what is this? Siemens something, simulation, motion. It seems like rigid dynamics, maybe an animation, maybe, yeah. Definitely not FEA. What is this? What is the purpose of this? What is this? Come on, no, please. What? No, not funny. All right, so air bearing based spacecraft attitude simulator instead of altitude. This could be interesting if there were balls and cages. Yeah, let me show you this simulation from 2 years ago. We have made a video of this. Also in static, yes. Yeah, it looks very nice. I like it. What is this? Improved bearing visualization. I would like to see it. Steel ball bearings draining through a narrow slit. Ah, yes. Small spheres. Yes. Why not? With motion view. I want to see this. We will stop at the second one, I think. Dedicated bearing, user interface improved. What? This is software. I think it's from the future, this software, 500 years in the future. Bearing, escape, rotor bearing. Yeah, it's rigid dynamics according to my assumption. Motion view, yes, I would have liked to see the rotating balls. I don't know if they rotate, maybe they rotate, maybe. No more bearings, no more bearings. Air bearing. All right, a roller bearing simulation. Yes. Let's approach second one. Let's approach. So the trade-off. The trade-off is like this. If we use a two quartz mesh and have enough nodes to contact each other, to match in the contact pairs. So sometimes if we don't have enough nodes, then either we have kind of sliding or contact does not appear. And this is why I would say that a quartz mesh can go so far, so it's not very advisable. But yes, we need to experiment. Or as you say it in FEA, trial and error is our daily bread. It's so heavy, such a bearing. So heavy. How can you? Someone should do spell check on the improvement and here on her improvement. This is something complex. Oh my god. This is a dream of mine to simulate in the future. It's very complex. A screw bearing. Oh my god. So complex. Let's go on GrabCAD and look for a screw bearing. no screw bearing for us? Or am I, I'm not writing it down correctly. Let's see. It's called, ball screw, okay. Ball screw. This is a dream of mine to simulate in the future. You have, but you don't have the balls. So yeah, it's not so easy to find a good 3D model and complete and without errors. This is why maybe I didn't simulate until now. You can ask yourself, hey Cody, why didn't you model? And I don't want to put the time, the effort in modeling. I want to put the effort mainly on simulation and less on modeling. Even though today I modeled my bearing from scratch, from zero. Come on, let's see a ball screw. What? Why does this look good? I'm not expecting it to look good. So look here, this ball is penetrating here. It's a collision. And this means we need, all the balls, they collide. Let's download the file because it, I think. The files, more files, all right, and like 90% of the models on GrabCAD are almost useless, and they require many editing and reconfiguration and healing, and yeah. So what we have here, nothing. Cut part. How can you make a cut part from an assembly? All right. So section view. Do we have the balls? No, nothing. No. Come on. The one that everyone hates on GrabCAD. Assembly file without parts, which is useless. Step. Zero use. Step. Section. No balls. No balls. Travel step. What? Too few people. No balls. Why don't these dudes have balls? Another assembly file without parts, which is completely useless. Oh my god, not useful. Yeah, they are free, but I cannot contest too much. Let's order by most liked. Misumi bar. Look how much collision. Maybe it's meant to simulate the thread. No balls. Ball screw. Linear actuator. So the nice renders get most likes and comments, but inside this looks promising. This looks promising. This is only the knot, if I see correctly. Section. I don't want to look more. Ball, knot, ball. Step. This is the entire assembly, I think. Section X. X is good. No ball, no. Step. Step. Come on, reach one, please. Please reach one. We have some balls here. We don't care about this bearing which is fused, but we have some balls here. The balls are, as I said in the past, two big balls, let's say. They are colliding, they are overlapping. Come on, no. This is promising. Promising and no cigar. IGS. What IGS is this? Download. Yeah, let's like it, even though he didn't provide a solid model. I think let's open SpaceClaim and evaluate what our colleague did. The full simulation. Yeah, very, very nice, very nice. Yes, hit one, come on. Let's open the IGS. And see what surprises we have inside. Come on, show us. These are solids. These are solids. Oh my God, something useful. Finally, something useful. Design section view according to. Can I select? No. Why can I not assign an axis? Axis. Section plane according to this axis. All right, and now let's view. Oh, even though we have collisions, this is a useful field. I'd like to use it. Oh my God, finally something useful. We will fix something and rotate and push something. Yes, I will let this free and rotate this shaft, and it will translate this. Yes, very nice. Finally, something good. I don't know if it's correct, but I'll name it screwball V1. All right, so ladies and gentlemen, we are interrupting this simulation after step 1. Let's look for questions if there are. Yes, this may be a basic question. Let's say I have accidentally pressed the stop button. Is it possible to continue? Okay. Is it possible to continue the simulation without restarting from the beginning? I normally have to restart again. I would say no. I would say no. I swear. I would say no. Maybe there is a restart file, but restarts are created when we press pause. Sit is sit. Oh, I said sit. Sit. Okay. Save. Let's see what we have. Let's see what we have. So let's have rotation. Please give us rotation. Yes. It's it's a work in progress. You know what? It's a work in progress. The balls rotate. It's a work in progress. Yes. That's for 2 hours of work. It's it works. Some strain. Not so nice. Pretty erratic. Oh my God! What is this? Yeah, so you have used some method. You have viewed some methods. Let's remove edges. Oh, these look nice. It's clear to me now that I think I have different, no. Because I have different friction coefficients. Here I have 0.3 and here 0.1, if I remember correctly. This is why we have more friction here, more frictional stress. The same with pressure, I think. Yes. I see that maybe the cage is restraining too much because I see too much pressure here. I think I should have left a bigger gap inside the cage. Yes, ladies and gentlemen, let's finish it for today here, and let's search for other questions or something else. We will end the stream here. Thank you very much for your patience, and meet you very soon in a few days. Thank you. Bye-bye.